Section 20.2, Balancing Oxidation Reduction Equations. We know that whenever we balance a chemical equation, we must obey the law of conservation of mass. The amount of each element must be the same on both sides of the equation. As we balance oxidation reduction reactions, we'll see an additional requirement. The gains and losses of electrons must be balanced. In other words, if a substance loses a certain number of electrons during a reaction, then another substance must gain that same number of electrons. In many simple chemical reactions, such as equation 20.2, this balance of electrons is handled automatically. We can balance the equation without explicitly considering the transfer of electrons. However, many redox reactions are more complex than equation 20.2 and cannot be balanced easily without taking into account the number of electrons lost and gained in the course of the reaction. In this section, we'll examine a systematic procedure for balancing redox equations. Half reactions. Although oxidation and reduction must take place simultaneously, it's often convenient to consider them as separate processes. For example, the oxidation of tin by iron. Tin 2 cation plus 2 iron 3 cations will yield a tin 4 cation plus 2 iron 2 cations. Can be considered to consist of two processes, the oxidation of tin and the reduction of iron. In the oxidation, we have tin 2 cation yielding a tin 4 cation plus 2 electrons. In the reduction of iron, we have 2 iron 3 cations plus the 2 electrons yielding 2 iron 2 cations. Notice that in the oxidation process, electrons are shown as products. In the reduction process, electrons are shown on the reactant side of the equation. Equations that show either oxidation or reduction alone, as in equations 20.4 and 20.5, are called half reactions. In the overall redox reaction, the number of electrons lost in the oxidation half reaction must equal the number of electrons gained in the reduction half reaction. When this condition is met and each half reaction is balanced, the equation on each side cancel when the two half reactions are added to give the overall balanced oxidation reduction equation. Balancing equations by the method of half reactions. The use of half reactions provides a general method for balancing oxidation reduction equations. As an example, let's consider the reaction that occurs between the permanganate ion and the oxalate ion in acidic aqueous solutions. When permanganate is added to acidified solution of oxalate, the deep purple color of the permanganate ion fades, as illustrated in figure 20.2. Bubbles of carbon dioxide form and the solution takes on the pale pink color of magnesium. We can therefore write the unbalanced equation as follows. Permanganate ion, aqueous, plus oxalate ion yields manganese ion plus carbon dioxide. Experiments also show that hydrogen ion is consumed and water is produced in the reaction. We will see that these facts can be deduced in the course of balancing the equation. To complete and balance the equation 20.6 by a method of half reactions, we begin with the unbalanced reaction and write two incomplete half reactions, one involving the oxidant and the other involving the reductant. Permanganate yielding manganese and oxalate yielding carbon dioxide. We have not explicitly stated which substance is oxidized and which is reduced. This information emerges as we balance the half reactions. We can now complete and balance the half reactions separately. First, the atoms undergoing oxidation and reduction are balanced by adding coefficients on one side or the other as necessary. Then the remaining elements are balanced in the same way. If the reaction occurs in acidic solutions, hydrogen ion and water can be added either to the reactants or to the products to balance hydrogen and oxygen. Similarly, in basic solution, the equation can be completed using hydroxide and water. These species are in large supply in respective solutions, and their formation as products or their use as reactants can easily go undetected experimentally. In the permanganate half reaction, we've seen that one manganese atom on each side of the equation. However, we have 4 oxygens on the left and none on the right side. 4 water molecules are needed among the products to balance the 4 oxygen atoms in permanganate. Permanganate yields manganese plus 4 water molecules. The 8 hydrogen atoms that this introduces among the products can then be balanced by adding 8 protons to the reactants. 8 protons plus permanganate yields manganese plus 4 water molecules. There are now equal numbers of each type of atom on both sides of the equation, but the charge still needs to be balanced. The total charge of the reactants are 8 times 1 plus -1 yields plus 7, and that of the products is plus 2 plus 4 times 0 equals plus 2. To balance the charge, 5 electrons are added to the reactant side. Although the oxidation numbers and the elements need not be used balancing half reactions by this method, oxidation numbers can be used as a check. In this example, permanganate contains manganese in a plus 7 oxidation state. Because manganese changes from a 7 to a 2 oxidation state, it must gain 5 electrons, as we've just concluded. 5 electrons plus 8 protons plus permanganate yields manganese plus 4 waters. For the oxalate half reaction, we must first realize that the mass balance requires the production of 2 carbon dioxide molecules for each oxalate ion that reacts. Oxalate breaks into 2 carbon dioxide molecules. Mass is now balanced. We can balance the charge by adding 2 electrons to the products, giving a balanced half reaction. Oxalate yields 2 carbon dioxide molecules plus 2 electrons. Now that we have 2 balanced half reactions, we need to multiply each by an appropriate factor so that the number of electrons gained in one half reaction equals the number of electrons lost in the other. The half reactions are then added to give the overall balanced equation. In our example, the permanganate half reaction must be multiplied by 2, and the oxalate half reaction must be multiplied by 5 so that the same number of electrons, 10, appears on both sides of the equation. 10 electrons plus 16 protons yields 2 permanganate ions, yielding 2 manganese ions plus 8 water molecules. 5 oxalate ions yields 10 carbon dioxide molecules plus 10 electrons. Add them together, and you get 16 protons plus 2 permanganate ions plus 5 oxalate ions, yielding 2 manganese ions plus 8 water molecules and 10 carbon dioxide molecules. The balanced equation is the sum of the balanced half reactions. Notice that the electrons on the reactant and product sides of the equation cancel each other. We can check the balanced equation by counting the atoms and charges. There are 16 protons, 2 manganese, 28 oxygens, 10 carbons, and a net charge of positive 4 on both sides of the equation, confirming that the equation is correctly balanced. We can summarize the procedure that we use to balance a redox reaction that occurs in acidic solution. 1. Divide the equation into 2 incomplete half reactions, one for oxidation, the other for reduction. 2. Balance each half reaction. A. First balance the elements other than hydrogen and oxygen. Next, balance the oxygen atoms by adding waters. Then, balance the hydrogen atoms by adding protons. Finally, balance the charge by adding electrons to the side with the greater overall positive charge. 3. Multiply each half reaction by an integer so that the number of electrons lost on one half reaction equals the number gained in the other. 4. Add the 2 half reactions and simplify where possible by canceling species appearing on both sides of the equation. 5. Check the equation to make sure that there are the same number of atoms of each kind and the same total charge on both sides. Balancing equations for reactions occurring in basic solution. If a redox reaction occurs in a basic solution, the equation must be completed by using hydroxides and waters rather than protons and waters. The half reactions can be balanced initially as they occurred in acidic solution. The hydrogen ions can then be neutralized by adding an equal number of hydroxides to both sides of the equation. This procedure is shown in sample exercise 20.3.